Hello, everyone. Good morning. Sorry, I think there's an... All right. Hello, everyone. Good morning. My name is Juan. I'm an electronics engineer from Buenos Aires in South America. I would also like to mention Julian, which is actually my boss, and push this work forward. I work for Ecumen, with headquarters also in Buenos Aires in Argentina, but part of our team is also distributed throughout the country and also in Paraguay, also in South America. We provide the software consultancy services to our customers, which are mainly in the US. And I would also like to mention Intermodalix, which is a company in Belgium, and well, a small company called Google, perhaps you know it, which both helped us with this project. So the purpose of this talk is to answer you some questions such as why would you choose Android as an alternative platform to build a robot on? What are the tools and libraries that are available there, and how much will it cost you in terms of development hours and effort? We will also be presenting TangoBot, which is a robot that is powered by a single Android device, which is a ready-to-use example. So the first reason is technological. If you take a look back at the first Android phone and the currently available Android phones, we'll see that there's a huge improvement in terms of processing power, memory size, sensor capabilities, networking capabilities, and I could just use the whole talk to fill the list. So all these improvements make robotics application actually, make these phones actually suitable for robotics applications. The second reason is mainly social. Basically, if you see this chart, Android phones are extremely popular throughout the world. And in fact, it's nowadays the most popular operating system if you take into account both desktop and mobile devices. And this is good for two reasons. The first one is that the market is huge. Lots of millions of cell phones are sold every year, and people are really used to it, so it's a good opportunity for robotics to get into a wide consumer market. And the other reason is because this huge demand in devices pushes the manufacturers to put more and more technology into the devices. So you will get the latest processors that are actually pretty efficient. Perhaps a phone is not as powerful as the servers that the PR2 had, but they definitely consume much less and are much more efficient. And they already have enough processing power for your applications. Another interesting thing is that with the Google Play Store, you will have all the deployment system that you need, which is actually really cool for distributing your software and also collecting data from your users. So going to the second question, how do you do this? Well, the first obstacle that you will encounter is that, well, Android actually runs on Java, so you won't be able to run ROS packages as they are. Also, Python packages won't be available. But you actually don't need to rewrite the whole ROS from scratch. In 2012, Damon Kohler, who I think is around here, presented ROS Java, which is a complete re-implementation of ROS in Java. So that will basically give you access to nodes, services, parameters, everything that you need is there. With that, you are just ready to start writing your own nodes and executing them on Android. The second part, which is also important in ROS, are the libraries. Basically, you don't have the same package availability, but there are some tools that will help you cross-compile packages and run them on Android. A few years ago, Gary Serwin, who is actually my colleague, presented ROS CPP Android, which is a public repository that has a receipt that will help you cross-compile packages so that you can run them on Android. Basically, you just will follow this receipt. You will get a list of packages cross-compiled as shared objects that you can then link into your application. To do so, you will have to write a small wrapper around them, which are basically so that the cross-compiled libraries look like a native node. Native nodes are actually a component of ROS Java, and then you will just execute those native nodes as if they were regular ROS Java nodes. Behind the scenes, native nodes use JNI, which stands for Java Native Interface, to call the native code. So that will give you access, for example, to interesting packages such as MoveBase and much others. Also, this work has had some contributions in the recent past to support, for example, plugin-lib and other interesting libraries, which are certainly useful in robotics development. The third tool that you will have is Maven, which is basically the place to share Java libraries. ROSJava actually hosts one Maven repository, and that allows users to publish Java compiler artifacts, and then with that you can just include those libraries into your application just by adding simple lines to your build script. Another interesting fact is that we are using Gradle to build the application, and that's integrated with Calkin. So in the end, ROSJava and Android package will look just as a regular ROS package that you can build with Calkin Make. So all this theory looks nice, but perhaps you're already wondering, where's the robot? So let me present you the TangoBot, which is an Android-powered robot. It's a Turtlebot spin-off. Basically, we have replaced the laptop for a single Android phone, which does all the processing and also has all the sensors. In this case, we are using a Tango-enabled device. We will get to that because of the interesting sensors that it provides. The purpose of the TangoBot is a research platform and also to show that Android can drive a robot, and all of its components are open source. So I would like to show you a video about this. In the video, you can see, well, that's me. I'm teleoperating the robot from a client application. The phone that is on the robot is actually doing all the work from the client application and just visualizing the robot. We are using for now an empty map. Using a global map is actually something that has to be done yet, but it certainly can be done. Those black stains are actually the local obstacles that the robot is seeing using its sensors. And now all of that is the navigation stack. The obstacles are a bit inflated by the inflation layer of the navigation stack. You can see that in the client library, I also have access to the camera, which is pretty interesting. When I tell the robot to come back by giving it a goal, you will see its amazing dodging skills with that computer. Yeah, awesome. Okay, that's with the video. So now we would like to review a little bit the hardware and the software components of the robot. From a generic point of view, any autonomous robot basically needs a perception system, such as sensors like cameras, IMUs, and so on, lasers, whatever you want. A processing unit to process all the information coming from the sensors and from the user input. And then an actuator, which is basically the mobile base to take the robot where it has to go. So if we compare to the standard Turtlebot, we basically remove the laptop, remove the laser scan, the Kinect sensor, and we replace all that with a Tango-enabled phone. You don't actually need a Tango-enabled phone to run your own robot, because with the USB of the phone, you can actually drive whatever sensor you want to include. In this case, we thought it was convenient because we already had all the sensors we needed in a single device. So we actually didn't need to add another device. So if we now dive into the software, you will see that from top to bottom, we have first the application, which is basically an Android user interface to show the status of the robot and so on, to configure some things such as the ROS master URI and so on. And it's also a node launcher. In ROSJava, you can launch as many nodes as you want from a single application. So it's a sort of big launch file. Then it goes the navigation stack, the drivers for the sensors, and the drivers for the mobile base. Let's take a look at these components one by one. From a generic point of view, the navigation stack, for those who are not familiar with that, basically takes sensor input and user input and translates it into velocity commands that the mobile base will interpret and execute. The navigation stack is a pretty complex piece of software, and it's pretty flexible and configurable. It has many components such as cost maps, planners, and recovery behaviors. And recoding all that from scratch in Java is actually a big piece of work, and nobody wants to do that. So this is a perfect use case scenario for ROS CPP Android. The move-based package that is regular for ROS can be cross-compiled and then wrapped into a native node, which can be executed by the TangoBot application. So in this case, what we only have to do is write all those theme wrappers, cross-compile the package, and then we are ready to use it in our application. So now we would like to give a few words about Tango, which is the perception system that we are using in this case. Tango is a software and hardware stack that has 3 key features, which are motion tracking, area learning, and depth perception. This is all about giving the device capabilities to understand its surroundings a little bit better than regular devices. So with motion tracking, you will get visual inertial odometry. Area learning will complement that by learning features in the environment and localizing against those features. And depth perception is all about the shape of the objects that are around the device. And that will help you, in particular, with obstacle avoidance. So how does all this relate with ROS? Well, our friends at Intermodalics developed an application that actually gets the data from Tango and streams it into ROS by publishing it to regular ROS topics. The interesting fact about this application, which you can also download from the Play Store if you have a Tango-enabled device, is that the core is actually a ROS node that we could extract and then include in our application. It's also in ROS Java Maven's repository. So to include it in an application, you just have to add the dependency in your build script. So only with that, you have access to all the Tango information in ROS nodes, in ROS nodes and run ROS topics and messages. And so that's how we get point clouds, the pose of the robot, and also laser scans, which is pretty much everything we need for the perception system. Going one step down, we have the robot base driver, which is also an open source component called base controller. It basically translates the output of the navigation stack, which are twist commands, into serial commands that we can feed into a robot using the USB. And that's a pretty simple component. For now, it supports Kobuki bases, Husky, and iRobot create bases. We haven't integrated that part into the TangoBot applications yet, but it can be done certainly. And then I would like to talk about the next steps. As you have seen in the video, we are still using an empty map. So the plan is to sometime add a local map to use it and to navigate with. For that, we could use standard G-mapping algorithms by using the laser scan provided by the Tango ROS Streamer app. But we could also use some Tango features to build and navigate a map. That's also available in the Tango ROS node. We haven't integrated yet into the TangoBot application. Another interesting feature is to add more mobile bases to the supported ones, such as Turtle 3 and so on. You are all welcome to try out the code of the TangoBot and perhaps submit a pull request if you find anything, expand its features, and so on. All the code is open source and is already public in GitHub. So I would like to give you some closing thoughts about all this. When you are using Android to develop robots, you will find some challenges which are typically associated with limited package availability and perhaps, well, having to use multiple technologies such as multiple build systems, perhaps cross-compiling packages, and all of that. Perhaps it's a little bit confusing at first, but the good part is that there are plenty of tutorials around and we have some experience with it. And we also have TangoBot as a good starting point. So everything is documented out there. You can just check it out. The advantages are that the trend keeps on, and it indicates that in the future, Android phones will have even more technology and will still be even more popular. And that's a great opportunity for robotics to get into a wide consumer market and also make use of all that technology. Another good thing is that you have tools already. You don't have to write everything from scratch in Java. You can use ROS Java, you have cross-compiled packages, and so on. So there's a lot of knowledge and things that are already out there to get started with. So thank you very much for your time. This is a picture of our team, mostly up to date in Argentina. And we are really happy to help if you need anything with Android and robotics development. And I think it's now time for questions.
Thank you. Questions? Yes.
Hello. I have a question about the ROS Java, because the last time I used it, like 1 or 2 years ago, my experience is that the Maven repository was like half a year beyond the status of the apt repo for Ubuntu. So some message definitions changed, and I could not compile the workspace for the next half a year. So did this change to better?
Well, in fact, we are actually maintaining ROS Java in Ecumen. We are doing the best effort we can. We are also spending some time to maintain it and solve all those kind of issues. If you now open an issue, some of us will actually respond to it. It has some issues, but today it does its job. This is not, in fact, the only project I've been working with ROS Java. It does its job. And if you find anything, it can be solved.
But it still hasn't been accepted like the official ROS message generator, or has it?
Yeah, that's not exactly official, but perhaps my boss can answer that question better.
Yeah, we have other people here, like more official, that can probably answer too. But it's the only Java implementation that is widely used. It's like anything else in ROS. It's open source. It's the best we can do as a community. So if you want to know which is the right one to use, I think it's this one. If you are building something on Android, I can tell you that with security. We need you to help to make it better and more official that way.
Hope that answers the question.
What do you recommend if somebody wants to contribute into this ecosystem? Should they be taking things that are in C++ and NDK, compiling them over and wrapping them, or rewriting in Java? What do you recommend?
I think that depends on the case. If you have a complex piece of software, perhaps it's easier to add it to the receipt to cross-compile it as another package. That can be done. Like the recipe that I talked about, the ROSCP Android repo, actually, has a list of fixed packages that are cross-compiled. But you could add whatever you want there, so that's also, you could make a contribution there. Perhaps if the package is really simple, it is worth rewriting it on Java. So that would depend on the case, I would say.
All right. Well, thank you very much.